This is a carboxylic acid tutorial presented by the SHRDB with reference International in ASA Chemistry by Laurie Ryan and Roger Norris. Hello, this is a carboxylic acid tutorial. We start with the learning outcome. You should be able to explain the relative acidity of carboxylic acid of chlorine substituted ethanoic acid. We have described how some carboxylic acid such as methanoic acid and ethanoic acid can be further oxidized. Describe the reaction of carboxylic acid in formation of acid chloride. We have described the hydrolysis of acid chloride. Describe the reaction of acid chloride with alcohol, phenol, primary amine. Explain the release of the relative ease of hydrolysis of chloride, alkyl, and all that. So you can start. So now we need to know the acidity of carboxylic acid. We need to know that carboxylic acid is actually an acid, but it is a weak acid. Now there are different acidities of different carboxylic acid. The acidity of carboxylic acid is going to be directed via the degree of the polarity of the OH bond. The degree of polarity of OH bond is going to show you the degree of the acidity of a particular carboxylic acid. So we need to know that on a normal carboxylic acid with an alkyl group here, the polarity comes as a result of this O bond here and this double bond O. We need to know that oxygen is going to pull electron to this side. It's going to make this one to be much more delta positive. So we first start by oxygen from here is going to pull electron from hydrogen. And now this oxygen also here pulls electron from carbon. Since it pulls electron from carbon, it's going to cause more electron to be pulled from this oxygen, causing again more electron to pull from hydrogen and making this OH bond to be much more polarized. The more the OH bond is going to be polarized, the more there is going to be conversion from a covalent form to an ionic form, and the hydrogen ion is going to be released into the solution. So now, as in this form, so it's going to exist in this form. So now let's see a question. Let's have some questions. Example: what is the acidity of compare the acidity of ethanoic acid, chloroethanoic acid, dichloroethanoic acid, and trichloroethanoic acid? So what do you realize? You realize that when looking at each of these formulae, one chlorine molecule is going to be added to this CH2 group. Since one chlorine molecule is added to this CH2 group, it's going to pull, and chlorine is electronegative. So you see that there's going to be a pull of electron much more on this carbon atom, making this carbon atom to be much more delta positive. It's going to be much more positively charged. So it's going to pull again more electron from the OH, which is going to cause increased polarity again of this bond. So chloroethanoic acid is going to be more acidic compared to ethanoic acid. Now dichloroethanoic acid, with dichloroethanoic acid you have two chlorine molecules which are pulling each other. So since now there are two chlorine molecules, what do you realize? You realize that in this case the two chlorine molecules are going to even pull further. They didn't cause a delta plus here and pull again further and cause increased polarity of this OH bond. And lastly, we have trichloroethanoic acid. You see that it has three chlorine atoms which are going to pull again furthest. We are going to see it's going to pull again much more the electrons from carbon, which is going to pull, which is going to cause much more polarization of the OH group or OH bond. So you see that this molecule is going to be trichloroethanoic is going to be much more acidic compared to this other one, and the order is from top to bottom, least acidity to more acidic. As you can see here, you can see their Ka values. The greater the Ka of a substance, of a molecule, the greater the Ka of a molecule, then the more it is acidic. The greater the Ka, the more it's acidic. You can just see from the formula of Ka. Formula of Ka states that Ka is going to be equal to hydrogen ion times the concentration of the conjugate base divided by the concentration of oxalic acid. So you see that since hydrogen ion is going to be greater, it's going to be more form in this case, and there's going to be more conjugate base now, and there's going to be less conjugate acid. You see that the Ka is going to be larger. So that is just the explanation. Here you have one chlorine molecule that only pulls, so the depolarization. Here you have an alkyl group, and the alkyl group brings electron at this side. Here you have one chlorine molecule that pulls, so you're going to cause more depolarization. Here they have even two chlorine molecules that pull, much more depolarization, and three chlorine molecules that pull. You have further more depolarization of the bond. Now let's see oxidation of carboxylic acid. So we need to know that what carboxylic acid can be further oxidized to produce carbon dioxide and hydrogen. So in a positive test of aldehyde, the copper 2 ion in failing solution is reduced to copper 1 ion. When preceded, it produces red copper 1 oxide. When methanoic acid is oxidized by failing, the same positive test result is obtained. So the reason is because you have a hydrogen. When in case of methanoic acid, this result can be obtained because methanoic acid is having hydrogen and bonded to this carbon atom. Since hydrogen is bonded to this carbon atom, it can further go up to produce oxidation, and there's oxidation of this methanoic acid to produce carbon dioxide and water. But you need to know that what other carboxylic acids like methane, other carboxylic acid like methane, like other carboxylic acid like ethanoic acid, like butanoic acid, propanoic acid are not capable of being further oxidized. Only methanoic acid can be further oxidized to produce carbon dioxide and this hydrogen ion. So now these are the points. So and water. So now we also have another carboxylic acid, which is ethanoic acid. You can oxidize this methanoic acid. Was oxidized by using copper 2 ion, a simple reducing agent. But now this ethanoic acid can be oxidized too. This ethanoic acid can be oxidized too, though it does not have hydrogen that is bonded directly to it. So you can now here you are instead going to use a strong oxidizing agent to oxidize this ethanoic acid for acid. So now you have manganate, acidified potassium permanganate can be used. There you are going to have, you're going to convert to manganate to ion and produce carbon dioxide and water. So now let's speak about one derivative of the carboxylic acid called acid chloride. So in order to name an acid chloride, just take the name, just name the compound as if you are naming a carboxylic acid, and then you add you remove oic acid, and then you instead oil chloride. So in this case, this is an ethanoic acid. You instead add oil chloride and you have ethanoyl chloride. So in this case again, this is this is benzoic acid. You add instead oil chloride at the end to have benzoyl chloride. So those are the names. So now let's visualize now the next point. So how do you form acid chloride? You can form acid chloride by using phosphorus pentachloride. You use phosphorus pentachloride, you use phosphorus trichloride, or you use sulfur dichloride oxide. You use sulfur dichloride oxide. So all of them are capable of being used to form a acid chloride. But phosphorus pentachloride is going to produce fumes of hydrochloric acid, and also with sulfur dichloride oxide is also going to produce fumes of hydrochloric acid. So it's also going to produce fumes of hydrochloric acid and sulfur dioxide. So these two are used as a test to find if the OH group is present inside a compound. So since the ethanoic acid or carboxylic acid has the OH group, so these are going to be fumes of hydrochloric acid are going to be emitted from this pentachloride and sulfur dichloride oxide. Now you have the next point. You have carboxylic acid with phosphorus trichloride. In this case, you produce the ethanoic chloride and you produce phosphorus acid. So now the next point, you have benzoic chloride. Benzoic chloride can be produced from benzoic acid. If you do the same thing here with benzoic chloride, instead going to with benzoic acid, with this reaction, you're going to produce benzoyl chloride. So now these are the points. So now we need to know the general reaction of ethanoic chloride. The general reaction of ethanoic chloride is that ethanoic chloride reacts with a certain HZ to produce ROZ plus HCl. That's the general formula for reaction of ethanoic chloride. So now let's visualize that. Example, you have hydrolysis of acid chloride. You see that as this hydrolysis, you see that it's made up of HOH. So now since it respects this formula of HZ, the Z there is going to be OH. This O is going to replace this Cl, and then you are going to have this CH3, CH2, COO. You just replace OH at the place of Cl. You have propanoic acid plus HCl. So that's the general formula that you use in order to derive the molecules that are formed from ethanoyl chloride. So now example here, this is the mechanism of action. See that water, this molecule is going to pull the OH to its side, and this chlorine molecule is going to pull OH to its side. But now you see that water is going to enter, is going to, since oxygen has two lone pairs of electron, one lone pair of electron is going to bond to this carbon atom, since this delta plus, since delta plus again, you see that chlorine now is going to take electron further away and move out, and this molecule is going to lose one hydrogen. One hydrogen is going to lose its electron to oxygen and produce a hydrogen ion. Hydrogen ion is going to go with this chloride ion to produce hydrochloric acid, and this molecule is formed. So that's a condensation reaction or an elimination reaction. So now let's visualize the next one. The ease of hydrolysis starting starting with compound most readily broken is, you need to know that what this is ease of hydrolysis. Acyl chloride is going to be greater than chloroalkane, is going to be greater than aryl chloride. So this is the ease of hydrolysis of any molecule. So this is how they as easy for you to hydrolyze a molecule. You need to know that what acyl chloride are very easy to hydrolyze. Then the next one are chloroalkanes, and then the last one are aryl chloride, the chlorides of the benzene ring. So now we have reaction of alcohols and phenols. So now with the reaction of alcohol and phenols, let's say with alcohols here, you see it's going to do the same thing. We have H2 and we have O. You need to know that respecting this formula still, the H here is given at this position here, and then the O is going to be O and CH2H5. So when you are going to find the total formula, going to at the end is going to, you just replace this Cl with CH2 and O, that then the final formula is going to give you ethanol. So now when you react let's say a phenoxide now with this molecule, this phenoxide now, you see that this Na is going to replace the H, so it's going to bind with this chlorine to produce that, and this O is going to bind to this molecule to produce phenylethanol. As easy as that. And also you have benzyl chloride plus sodium phenoxide. At the end you're going to have phenylethanol. As easy as that. Now reaction with amine. Reaction with amine is also easy. This amine has a lone pair of electrons. This lone pair of electrons is going to enter this position, and then it's going to lose one hydrogen. So that hydrogen is going to go out with the chloride ion to produce hydrochloric acid, and then N-methyl ethanamide is going to be produced, as we're going to see in the next chapter. So from here we have seen everything involved with acyl chlorides and carboxylic acid in compounds. So say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.